Have you ever noticed how some things seem to happen naturally, even without any effort? Ice melts in a warm room, smoke spreads out from a fire. These everyday occurrences might seem simple, but they point to a fundamental concept in physics: entropy. Entropy, in its most basic form, is a measure of disorder or randomness within a system. Think of it like this. Imagine a brand new deck of cards, all arranged neatly by suit and number. That's a state of low entropy, highly ordered. Now shuffle the deck, the cards become mixed up, their order randomized. That's higher entropy. The universe has a preference for states of higher entropy. It's not that the universe is inherently messy, but rather that there are simply far more ways for things to be disordered than ordered. Imagine searching for a single grain of sand on a vast beach. It's a needle in a haystack scenario. There are countless places for that grain of sand to be, representing high entropy, but only one precise location where it exists in perfect order. This tendency toward disorder isn't limited to decks of cards or grains of sand. It governs everything from the behavior of gas molecules in the air we breathe to the grand evolution of the cosmos itself. Entropy is, in a sense, the universe's clock, always ticking forward, driving systems from order to disorder. Let's bring this concept down to earth, or rather, into your bedroom. Imagine your room perfectly clean, clothes hung neatly, books aligned on shelves, not a speck of dust in sight. This is a state of low entropy, a triumph of order over chaos. But leave it unattended for even a short while, and what happens? Clothes end up on the floor, books pile up haphazardly, dust begins to settle. The room, seemingly of its own accord, gravitates toward disorder. This isn't because you're messy, though no judgment if you are, but rather because there are simply more ways for your room to be disordered than ordered. For every precisely placed item, there are countless positions where it could be slightly out of place. The same principle applies on a much grander scale. Imagine a supernova explosion, a star ending its life in a spectacular burst of energy. The star's carefully structured layers are blasted apart, scattering elements across the cosmos. This cosmic event dramatically increases the entropy of that region of space. Entropy helps us understand why broken eggs don't spontaneously reassemble, why ice cubes melt in your drink, and why the universe, from the Big Bang onward, has been in a constant state of expansion and change. It's a fundamental principle that underpins the very fabric of reality.
Know you've been a good friend, and that's in the thick and thin. And I know it's never
Now, this doesn't mean that order is impossible, just statistically improbable. Life itself, with its intricate structures and complex processes, seems to defy entropy. A single cell is a marvel of organization, with countless molecules interacting in a precisely choreographed dance, and yet, life exists within the framework of entropy, constantly battling against the tide of disorder. We expend energy to maintain our bodies, clean our homes, and build intricate structures, all in an effort to create pockets of order within a universe that leans toward chaos. The key to understanding this apparent contradiction lies in recognizing that entropy is a statistical concept. While the universe as a whole tends towards increasing entropy, localized decreases in entropy are possible, even common. These pockets of order, however, come at a cost. Just as it takes energy to tidy your room, it takes energy to build and maintain order in any system. The sun, for example, provides the energy that drives life on Earth, allowing for the creation and sustenance of complex, ordered systems. Entropy, then, is not simply a measure of disorder, but a key to understanding the delicate balance between order and chaos that governs the universe. It's a concept that touches every aspect of our existence, from the mundane to the magnificent, and its story is far from over. The story of entropy begins, as many scientific tales do, with a revolution. The Industrial Revolution, with its booming factories and clanking machines, had taken hold of Europe in the 19th century. Steam engines, those marvels of engineering, were transforming civilization, but their inner workings were still shrouded in mystery. Scientists sought to understand the fundamental principles governing heat and energy, and in their pursuit, they stumbled upon a concept that would reshape our understanding of the universe: entropy. At the forefront of this intellectual revolution stood Rudolf Clausius, a German physicist with a piercing intellect and a knack for unraveling nature's secrets. Clausius, like many of his contemporaries, was fascinated by the relationship between heat and work. He observed that heat, when applied to a system, could be harnessed to produce mechanical work, as seen in the chugging pistons of a steam engine. However, he also noticed that this process was never perfectly efficient. Some heat always seemed to dissipate, becoming unusable, lost to the surrounding environment. This realization led Clausius to a profound insight. He recognized that there was a fundamental asymmetry in the way heat behaved. While it was easy to convert work into heat, simply rub your hands together and feel them warm, the reverse process, converting heat into usable work, was always accompanied by losses. This fundamental irreversibility hinted at a deeper principle at play, a hidden accounting system governing the flow of energy in the universe. To describe this elusive concept, Clausius coined the term entropy in 1865, drawing from the Greek word trope for transformation. Entropy, he proposed, was a measure of the disorder or randomness within a system. The more entropy a system possessed, the more disordered it was. And crucially, Clausius postulated that the total entropy of a closed system, one that doesn't exchange energy with its surroundings, could only increase over time. This statement, known as the second law of thermodynamics, would become one of the most fundamental laws in all of physics. It provided a new lens through which to view the universe, revealing a fundamental directionality to time itself. Just as a dropped glass shatters into countless pieces, increasing the entropy of the system, so too does the universe, in a grand cosmic sense, march inexorably towards a state of greater disorder. Imagine a perfectly arranged library with books neatly categorized on shelves, a haven of order and knowledge. Now imagine that same library after a natural disaster, books strewn about haphazardly, shelves toppled, the once pristine order reduced to chaos. This, in essence, is the direction dictated by entropy, a relentless tendency towards greater disorder. Clausius's work provided a powerful framework for understanding the behavior of heat and energy, but it was not without its critics. Some physicists balked at the idea of a universe ruled by increasing disorder, a universe seemingly destined to end in a state of uniform randomness, a concept that would later be termed the heat death of the universe. The debate surrounding entropy was far from over. Enter Ludwig Boltzmann, an Austrian physicist with a bushy beard and a deep belief in atoms. At a time when the existence of atoms was debated, Boltzmann imagined the universe as tiny particles. Constantly colliding and interacting, his work revolutionized statistical mechanics, providing a microscopic explanation for macroscopic phenomena. Boltzmann argued entropy could be understood in terms of probabilities. A system with high entropy wasn't more disordered, but more probable. Think of a deck of cards. One way to perfect order, countless ways to shuffle. Imagine gas molecules in a container, zipping around and colliding. The system naturally tends towards a more probable, higher entropy state. Boltzmann's work explained why systems tend towards disorder. The concept of entropy, once confined to the realm of steam engines and heat transfer, began to permeate other areas of science. Physicists realized that the second law of thermodynamics had profound implications for the evolution of the universe itself. If the universe as a whole was subject to increasing entropy, then it stood to reason that it must have begun in a state of remarkably low entropy, a state of extraordinary order. This realization provided a crucial clue to the origin of the cosmos, hinting at a universe born from a state of unimaginable density and order, a state from which it has been expanding and evolving ever since. The Big Bang, with its initial conditions of extreme order and low entropy, became a cornerstone of modern cosmology, and the concept of entropy provided a crucial link between the universe's fiery birth and its ever-evolving present. From the microscopic dance of atoms to the grand evolution of the cosmos, the concept of entropy has profoundly shaped our understanding of the universe. It has revealed a fundamental directionality to time, a universal tendency towards disorder, and a deep connection between probability and the behavior of matter and energy. But the story of entropy doesn't end there. Its journey takes an unexpected turn in the 20th century, leading to new insights into the nature of information, computation, and the very fabric of reality. And that, as they say, is a story for another time. The Industrial Revolution, with its roaring factories and coal-powered engines, wasn't just about technology. It was a crucible for scientific thought. Amidst the clamor, thermodynamics emerged, studying heat and energy. Central to this was entropy, a measure of disorder, changing our universe's understanding. Thermodynamics is about energy, its transformation and transfer. Imagine a steam engine, coal burns, heat transforms water into steam, pushing a piston. This process, from heat to motion, is governed by fundamental laws with entropy at the center. The second law states that entropy in a closed system can only increase over time. While energy is conserved, its usefulness diminishes, tending towards equilibrium and maximum entropy. To grasp the essence of entropy, we need to peer beyond the macroscopic world of steam engines and coffee cups and delve into the microscopic realm of atoms and molecules. Imagine a sealed container filled with gas, a jumble of countless particles, each zipping around at unimaginable speeds, colliding with each other and the container walls billions of times per second. Each collision, each interaction, represents a tiny exchange of energy, a microscopic dance that dictates the overall state of the gas. Now imagine for a moment that all those gas molecules, by some cosmic coincidence, were to suddenly congregate in one corner of the container, leaving the rest empty. This highly ordered, low-entropy state is theoretically possible, but in reality, it's about as likely as winning the lottery every day for a year. Why? Because there's only one way for the molecules to be perfectly arranged in that corner, but trillions upon trillions of ways for them to be dispersed throughout the container. Entropy, in this sense, is a measure of probability. The more possible arrangements a system has, the higher its entropy. And in the chaotic world of molecules, disorder reigns supreme. Think of a deck of cards. There's only one way to arrange them in perfect order, but countless ways to shuffle them into a random high-entropy state. The same principle applies to the molecules in our gas-filled container, or the air we breathe, or the water in a glass. Disorder, statistically speaking, is the most likely outcome. The second law of thermodynamics, with entropy as its cornerstone, has profound implications for the way we understand heat, work, and the very nature of reality. It tells us that every time we try to harness energy, to transform heat into motion, or light into electricity, we inevitably pay a price measured in increasing entropy. Consider a car engine. We burn fuel, releasing heat that expands gases, pushing pistons and ultimately turning the wheels. But not all the heat generated by the burning fuel is converted into useful work. Some of it is lost as heat radiating from the engine, some is lost to friction between moving parts, and some is lost in the very process of combustion itself. This inherent inefficiency isn't a sign of poor engineering, but rather a fundamental limitation imposed by the second law. The more entropy increases in a system, the less useful work we can extract from it. It's as if the universe is constantly levying a tax on our energy transactions, a tax paid in the currency of disorder. This principle applies to every process in the universe, from the smallest chemical reactions to the grandest cosmic events. It's why batteries eventually run out, why stars eventually burn out, and why the universe itself, in the distant future, might end in a state of maximum entropy, a state of uniform temperature and maximum disorder, where nothing more can happen. Entropy explains why ice melts, black holes form, and time flows in one direction. Dropping an ice cube into water increases the system's entropy, a process that's irreversible. When a massive star collapses into a black hole, its entropy dramatically increases, creating a singularity from which nothing can escape. Entropy offers clues to the arrow of time, explaining why we remember the past but not the future. Watching an egg shatter shows entropy's unidirectional flow, from order to disorder. This connection between entropy and time's arrow hints at deep links between thermodynamics and the nature of reality. The 20th century saw breakthroughs connecting information and thermodynamics. Claude Shannon's 1948 paper laid the foundation for information theory, using entropy to quantify uncertainty. Shannon showed that information reduces uncertainty, much like entropy measures disorder. Claude Shannon, driven by curiosity, revolutionized communication. He bridged fields, seeing connections between thermodynamics and information. Shannon adapted entropy to quantify uncertainty in messages, showing that more unpredictable messages carry more information. His insights laid the groundwork for the digital age. Shannon introduced the bit as the fundamental unit of information. A bit represents the information gained from an event with two equally likely outcomes. High-entropy messages have many possibilities, conveying more information. Shannon's work showed that channel capacity is limited by noise and message entropy. Shannon's insights led to practical applications like error-correcting codes and data compression. Error-correcting codes protect information from noise by adding redundancy. Data compression algorithms use entropy to represent information efficiently. Shannon's work underpins the digital age, guiding advancements in AI and quantum computing. Entropy's influence extends to cryptography, biology, finance, and cosmology. Cryptographers use entropy to create secure encryption algorithms. In biology, entropy shapes processes like DNA replication and protein folding. Economists use entropy-based models to understand market volatility and risk. Cryptographers use entropy to transform messages into secure random sequences. High entropy in encrypted messages makes them difficult to crack. Entropy protects digital secrets, ensuring confidentiality against adversaries. Entropy shapes biological processes, introducing randomness into DNA replication. Mutations, often harmful, can also be beneficial, driving evolution. Entropy introduces genetic diversity, essential for natural selection. Even in ordered systems, randomness plays a crucial role in life's complexity. Complex systems like weather and markets exhibit emergent behavior, defying prediction. As systems become more complex, their entropy increases, making them less predictable. Predicting the behavior of trillions of interacting molecules illustrates this challenge. Entropy sets a fundamental limit on our ability to forecast the future. Section 5. Investing in disorder entropy and the financial markets. The financial markets, with their constant fluctuations, might seem like an unlikely place to apply the principles of physics. Yet, a growing number of economists and investors are turning to entropy to understand market volatility and risk. Traditional models assume markets are efficient and rational. However, the reality is far more complex. Markets are driven by human behavior, with all its biases and emotions. This unpredictability can be better understood through the lens of entropy. Entropy measures uncertainty or disorder in the market. High entropy means high volatility with rapid price changes. Low entropy indicates a more stable and predictable market. Entropy-based models help quantify market risk and inform asset allocation. By analyzing historical data, these models provide insights into future market movements. Entropy-based approaches offer a fresh perspective on navigating financial complexities. Acknowledging uncertainty helps investors make more informed decisions in finance. From the smallest subatomic particles to the largest cosmic structures, the universe is engaged in a perpetual dance of energy and matter, governed by the laws of physics. The second law of thermodynamics dictates ever-increasing entropy, leading to a state of maximum disorder. This is often referred to as the heat death of the universe. Stars will exhaust their fuel, galaxies will drift apart, and the universe will become a cold, dark expanse. However, our understanding of its fate is far from complete. Some speculate our universe might be one of many in a multiverse, each with its own entropic destiny. The question of the universe's ultimate fate remains profound and unanswered. We've journeyed from the heart of the atom to the edge of the observable universe, all in pursuit of a single elusive concept: entropy. It's a concept that defies easy definition, yet its influence is woven into the very fabric of reality. It's the subtle force that drives ice to melt, whispers in the hiss of static, and dictates the direction of time's arrow. Entropy speaks of disorder, of the universe's tendency to unravel from the intricate to the mundane. It reminds us that the natural order of things is not towards perfection, but towards an eventual state of equilibrium, where energy is evenly dispersed, and the potential for work, for change, diminishes to nothingness. Think of a magnificent sandcastle, painstakingly built grain by grain, only to be reclaimed by the tide, or a symphony, its final notes fading into the silence from which they came. These are echoes of entropy, reminders that even the most elaborate constructs, the most breathtaking moments, are ultimately fleeting in the grand scheme of the cosmos. Yet, to see entropy only as a harbinger of decay, a cosmic force pushing towards oblivion, is to miss its deeper significance. It's in the unwinding, in the constant shuffling of energy and matter, that the universe finds its dynamism. The emergence of life, with its breathtaking complexity and improbable order, seems to stand in defiance of entropy's reign. A single cell, a marvel of miniature machinery, is a testament to the universe's ability to create islands of order amidst the ever-increasing chaos. But even life, in its tenacious grip on existence, cannot escape entropy's embrace. It's there in the mutations that drive evolution, in the aging process that marks the passage of time, in the eventual return of all living things to the fundamental elements from which they came. Life, then, is a delicate dance, a constant struggle against the tide of disorder. We expend energy to maintain our bodies, to build shelters, to create societies, all in an effort to carve out pockets of order within a universe that seems hell-bent on shuffling everything back into a homogeneous soup. And yet, what a glorious gamble it is. Life, in its very impermanence, finds its preciousness. It's the fleeting flame that illuminates the darkness, the intricate pattern woven into the fabric of existence, a testament to the universe's boundless capacity for creativity, even within the constraints of its own laws. The study of entropy is not just about understanding the universe's inevitable decline, it's about unraveling the deep connections between energy, information, and the very nature of reality. It's a journey that has led us from the steam engine to the black hole, from the telegraph to the genetic code, revealing a universe far stranger and more wondrous than we could have imagined. As we stand at the precipice of the 21st century, armed with the insights gleaned from centuries of scientific inquiry, the concept of entropy continues to challenge our assumptions and push the boundaries of our understanding. It raises profound questions about the nature of time, the limits of knowledge, and the ultimate fate of the universe itself. We don't have all the answers, and perhaps we never will. The universe, in its infinite complexity, delights in throwing us curveballs, reminding us that the more we learn, the more we realize how much remains unknown. But that's the beauty of science and indeed of life itself. It's in the pursuit of knowledge, in the exploration of the unknown, in the constant questioning and re-evaluating that we find our greatest rewards. Entropy, with its paradoxical blend of order and chaos, reminds us that the universe is a dynamic, ever-evolving canvas, and we, as conscious beings, have the extraordinary privilege of witnessing its unfolding story.